Hi everybody, I'm Dr. Matthew Turner with the Electrical and Computer Engineering Technologies program at Purdue University in New Albany, Indiana, and you're watching a video lecture for ECET 273 Modern Energy Systems. This is the course introduction, and this is a course that introduces you all to the technologies used in the electric power grid. Topics that we'll cover are going to include just broadly energy conversion fundamentals. How do we convert fuels into electrical energy and the efficiency of those methods. We're going to look at renewable energy technologies such as wind, solar, geothermal, tidal maybe. Other topics that we'll cover will include the electric grid, including central and distributed generation plants, power plant fundamentals, transmission and distribution lines, and then we'll also look at kind of how people use electricity at their homes, in businesses, in factories, and how machines use electricity, so what we call the end use of electricity. This video is part one of part two that's really going to focus on energy, force, and power, the relationships between those quantities. It's pretty important for modern energy systems that we understand energy, force, and power. Let's really begin with a brief overview of really the major course topics covered in ECET 273 Modern Energy Systems, and how we're going to do that is first give a broad overview of what's going on in the electric grid. So an electric power system is the network of interconnected electrical devices that we as a society use to source electric energy, to transmit that electric energy from the places that it's made to the end customers, and then all the devices connected that use electric energy. So all together those things are really called the electric power system. When an electric power system is used to supply a region of homes and industries with electric energy from power plants, we usually call this power system an electric grid, and it's divided into three parts, right? So this electric grid consists of three things broadly. I mean, there's a lot more in it than just three things, but broadly there's three classes. There's generators that are the sources of electric energy. There is the network of wires that carry the electric energy to the customers. We call this transmission and distribution wires. They carry the power from the generators to the customers. And finally, we've got the load devices that use electric energy to do work. Just in this diagram that you guys are seeing here, we've got a couple examples of generators. We've got coal plants here, hydroelectric plants, nuclear plants. Sometimes industrial facilities will have the ability to produce small amounts of electricity. We call those industrial power plants. And then also, you know, you have your renewable energy resources, your wind, your solar, maybe some small-scale hydroelectricity, things like that. Those are the power plants, right? These different color wires in the diagram, those are representative of the transmission, which is on the left side here. Those are the higher voltages. Those are the wires, the towers, the substations that operate at extra high voltages or high voltages, and those are the wires that operate at kind of lower voltages. And then finally, we've got the end use. What we show end use here is we just show customers' houses. What we really mean by that picture is we mean the light bulbs inside the houses, the computers, you know, the air conditioners. Some people have electric heating, you know, resistive baseboards. Or maybe those are motor loads, refrigerators, compressors, you know, things like that. Inside factories, there might be other, you know, bigger motor loads or things like that. So those are the end uses of electricity. The North American grid in the United States, and also it connects to Canada, so we kind of consider it one grid. It consists of really thousands of these generators of different types that provide electricity to literally millions of people via a vast network of wires. I mean, millions of miles of wire. This thing is huge. These generators are often located remotely away from cities. You know, we want to get them out of town. They produce a low voltage. The output voltage of these generators in terms of power systems is low. It's at 20 kilovolts or 20 kV. Those low voltages are then stepped up at the generation to some higher voltage for transmission. We're going to say usually it's bigger than 69 kV if those voltages are traveling long distances. There are some, you know, special considerations that we'll look at over the course of this class, but really probably about 69 kilovolts to transmit over long distances. And that's done by these step-up transformers. Step-up transformers taking the generator voltages and increasing it to some sort of higher voltage. We then have some other transformers. This technically is a step-down transformer. It's taken an extra high voltage and reduced it from maybe 275 kV down to 110 kV. Then, more commonly, we'll see these step-down transformers at the interface between the transmission side and the distribution side. And the purpose of that is to reduce the distribution voltage, the voltage that's seen on the conductors in the distribution system, in populated areas down to like 4 to 35 kilovolts, so that it just has less risk of shock. It won't be as dangerous of a situation, right? Because these cables are near homes, near businesses, near trees and things like that. They run over your roads, so having them at lower voltages is just safer for all of us. They're also a little easier to work with if they're lower voltage. So it's stepped down, like I said, to between 4 and 35 kilovolts for distribution levels. And then really close to the customer, there's another step-down transformer that's going to reduce it down to 120 volts, single phase, 240, three-phase for use by us in our homes. That's what when we plug stuff into the wall, it's 120 volts for us residential customers. And then industrial customers, they get at different voltages because they usually have motor loads that require more power. So they get 277, 480 volts for a commercial building electric service. One of the things that is interesting is all of these parts in the system are electrically connected together, and they have to operate in what we call an electrical temporal balance, meaning the timing of the electricity over here is affected by the timing of the electricity here, is affected by the timing of the electricity here. There's a time relationship involved in all of this that we'll spend a lot of time investigating. And this kind of idea that everything is not only connected through electrical signals, but also the timing behavior of these electrical signals is called synchronism. It's a very important part of the modern electric power system. Another interesting thing is that because electrical energy must be produced by these generators at the same time it's being used over here. So as soon as I turn on a light switch over here, the power plant has to respond almost instantaneously or on demand. Most of the apparatuses in this system have to be in operation 24 hours a day and 365 days a year. So that, to me, is pretty amazing. And given that the North American grid is always on, always providing power to over 300 million people, you probably might understand why that the National Academy of Engineering has routinely ranked electrification of the United States as the top engineering achievement that has had the greatest impact on the quality of life in the 20th century. So it's really, electrification of the national grid is really just an amazing thing that we've been able to achieve as engineers. And in this class, you're going to learn all about what we just talked about. ECET 273, like I said, is an introductory course on modern energy systems. It's going to cover the following major topics. The first is how energy is converted from forms such as coal and sunlight into the electrical energy that's transmitted on the grid. We're then going to talk about the physics that govern charge, voltage, current, and power in alternating current systems. And we're going to look at how electrical energy is used to do useful work by the loads that are connected to the grid. After that, we're going to look at how electricity is carried from generators to customers, and we'll look at this over both short distances and long distances. They have some interesting design requirements depending on the length. We're then going to look at how electricity is measured and billed to customers. Right? You got to pay for this stuff. It's a business. We're going to then move on to system operation, or how and why system operators manage the flow of electricity on the grid. So there's these guys in control towers, and they make decisions about how the grid operates. We're going to look at their roles and how they make these decisions. We're going to briefly look at faults, kind of the causes of failure in electric grid and how to mitigate these events. We're going to look at something called power flow analysis, which is how to apply electrical engineering techniques and analysis to the flow of electrical current on the grid to kind of figure out what the voltages and currents are across the entire system. We're then going to look at emergent technologies, or how technology can make the grid more efficient, more reliable, more environmentally friendly. There's a lot of issues in the grid that are related to carbon and the mining of fuels and things like that. And a lot of these emergent technologies deal in those areas. Finally, we're going to look at government markets and regulations. These are the systems of government regulations and market factors that are going to influence system operation. One of the real interesting things about the electric power grid from an engineering standpoint is is that it is routinely influenced by decisions made by people who don't know much about the electric power system and the government, and then also economic factors, right? Prices of fuels, and there's electricity markets and things like that, that actually change the way that the system operates, because we try to operate it either for a, let's say, most power efficient, or maybe we're buying cheap electricity from someplace that made some bad decisions about fuel reserves or something like that. So they have to dump fuel into the market. And so, you know, there are market factors that will influence the operation of this.